CT stands for control transformer. A control transformer is a transformer that provides a lower voltage for control circuits. These control circuits are frequently used in systems such as lighting, heating, and ventilation. The primary function of a control transformer is to step down the voltage from a higher level, like 480 volts or 208 volts, to a lower, safer voltage of 120 volts or 24 volts that is suitable for power and control components. These control components can include relays, contactors, timers, and programmable logic controllers, also known as PLC. These devices need a stable and reliable power supply to operate correctly, and the control transformer provides this. Control transformers are designed to isolate the control circuits from the main power supply. This isolation is crucial for several reasons. Firstly, it enhances safety by preventing high voltage from directly entering the control circuits, which could pose a risk to personnel interacting with the system. Secondly, it improves the reliability of the control system by reducing the impact of voltage fluctuations and electrical noise from the main power supply. Control transformers also provide a degree of impedance, which helps to limit the fault current in the control circuit, further enhancing safety. The construction of a control transformer typically involves a primary winding which is connected to the main power supply, and a secondary winding which provides the low voltage for the control circuit. The core of the transformer is usually made of laminated steel to reduce eddy current losses and improve efficiency. The transformer is designed to operate at a specific frequency, usually 50 Hz or 60 Hz, depending on the power system standards. Control transformers come in various sizes and voltage ratings to accommodate different applications. The size of the transformer is determined by the volt-ampere, also known as voltamps, rating, which indicates the amount of power it can deliver to the control circuit. The voltage ratings specify the input and output voltages of the transformer. When selecting a control transformer, it is important to consider the total volt-amps of all the control components that will be powered by the transformer. It is also advisable to choose a transformer with a volt-amps rating that is slightly higher than the calculated total to provide a safety margin and accommodate any future expansion of the control system. Control transformers are widely used in industrial, commercial, and residential applications. In industrial settings, they are commonly used in motor control centers, also known as MCC, to power the control circuits for motor starters and other control devices. In commercial buildings, they are used in HVAC systems to power the control circuits for thermostats, dampers, and fans. In residential buildings, they may be used to power the control circuits for lighting systems and home automation systems. Installing a control transformer involves several steps. Firstly, the transformer should be mounted in a suitable enclosure that provides protection from environmental factors such as dust, moisture, and physical damage. Secondly, the primary winding should be connected to the main power supply using appropriately sized conductors and overcurrent protection devices such as fuses or circuit breakers. Thirdly, the secondary winding should be connected to the control circuit using similar wiring methods. It is important to follow all applicable electrical codes and standards when installing a control transformer. These codes and standards specify the requirements for wiring, grounding, and overcurrent protection. For example, the National Electrical Code, also known as the NEC, provides detailed guidelines for the installation of electrical equipment in various types of buildings. Maintaining a control transformer involves regular inspection and testing. The transformer should be visually inspected for any signs of damage such as cracked insulation, loose connections, or overheating. The voltage and current should be measured to ensure that the transformer is operating within its specified limits. The insulation resistance should be tested to verify that the insulation is in good condition. If any problems are detected, the transformer should be repaired or replaced as necessary. Control transformers are essential components in many electrical systems. They provide a safe and reliable source of power for control circuits, enhancing the safety and reliability of the overall system. By understanding the principles of operation, installation, and maintenance of control transformers, one can ensure that they function properly and contribute to the efficient and safe operation of electrical systems. Control transformers are designed with specific features to ensure their reliable operation. One important feature is the use of a fuse or circuit breaker on the primary side of the transformer. This overcurrent protection device is designed to protect the transformer from overload and short circuit conditions. The size of the fuse or circuit breaker should be selected based on the voltamps rating of the transformer and the voltage of the main power supply. Another important feature is the use of a terminal block or other type of connection device for the primary and secondary windings. These connection devices provide a secure and reliable way to connect the transformer to the power supply and the control circuit. The connection devices should be properly sized and rated for the voltage and current requirements of the application. Control transformers are also designed to operate within a specific temperature range. The operating temperature range is typically specified by the manufacturer and should be considered when selecting a transformer for a particular application. If the transformer is operated outside of its specified temperature range, it may experience reduced performance or premature failure. In some applications, control transformers are used in conjunction with other control devices, such as relays, contactors, and timers. These control devices are used to switch electrical circuits on and off based on various input signals. The control transformer provides the necessary power for these control devices to operate correctly. When selecting a control transformer for use with other control devices, it is important to consider the voltamps requirements of all of the devices. The transformer should have a voltamps rating that is sufficient to power all of the devices simultaneously. Control transformers are also used in applications where electrical isolation is required. Electrical isolation is the separation of electrical circuits to prevent the flow of current between them. This is important in applications where safety is a concern, such as in medical equipment and industrial control systems. Control transformers provide electrical isolation by physically separating the primary and secondary windings. There is no direct electrical connection between the two windings, so current cannot flow between them. This helps to protect personnel from electrical shock and prevents damage to equipment. In addition to providing electrical isolation, control transformers can also be used to reduce electrical noise. Electrical noise is unwanted electrical signals that can interfere with the operation of electronic equipment. Control transformers can reduce electrical noise by filtering out high-frequency signals. The transformer acts as a low-pass filter, allowing low-frequency signals to pass through while blocking high-frequency signals. This can improve the performance and reliability of electronic equipment. Control transformers are available in a variety of configurations. Some transformers are designed to be mounted on a wall or panel, while others are designed to be mounted on a DIN rail. DIN rail-mounted transformers are commonly used in industrial control systems. The configuration of the transformer should be selected based on the specific application requirements. Control transformers are also available with different types of enclosures. Some transformers are enclosed in a metal housing, while others are enclosed in a plastic housing. The type of enclosure should be selected based on the environmental conditions in which the transformer will be used. For example, a transformer that is used in a damp or wet environment should be enclosed in a waterproof housing. When selecting a control transformer, it is important to consider the efficiency of the transformer. The efficiency of a transformer is the ratio of the output power to the input power. A more efficient transformer will waste less energy and generate less heat. This can save money on energy costs and reduce the risk of overheating. Control transformers are typically tested and certified to meet various industry standards. These standards specify the requirements for safety, performance, and reliability. The most common standards for control transformers include UL, which stands for Underwriters Laboratories, and C, which stands for Conformité Européenne. When selecting a control transformer, it is important to choose a transformer that has been tested and certified to meet the applicable standards. This will help to ensure that the transformer is safe and reliable. In summary, control transformers are essential components in many electrical systems. They provide a safe and reliable source of power for control circuits, enhancing the safety and reliability of the overall system. By understanding the principles of operation, installation, and maintenance of control transformers, one can ensure that they function properly and contribute to the efficient and safe operation of electrical systems. Control transformers are identified by various specifications detailed on their nameplates. Understanding these specifications is crucial for selecting the appropriate transformer for a given application. Firstly, the volt-amps rating indicates the apparent power the transformer can deliver. This value is the product of the voltage and current and determines the transformer's capacity to power the control circuit. Secondly, the primary voltage specifies the input voltage the transformer is designed to accept. Common primary voltages include 120 volts, 208 volts, 240 volts, 480 volts, and 600 volts. It is critical to match the primary voltage of the transformer to the available power supply voltage. Thirdly, the secondary voltage indicates the output voltage the transformer will provide to the control circuit. Typical secondary voltages are 24 volts, 120 volts, and 240 volts. The secondary voltage must be compatible with the voltage requirements of the control devices. Fourthly, the frequency specifies the operating frequency of the transformer, typically 50 Hz with 60 Hz. It is essential to select a transformer with a frequency that matches the frequency of the power supply. Fifthly, the insulation class indicates the maximum operating temperature of the transformer's insulation. Common insulation classes include Class A, Class B, Class F, and Class H, each corresponding to a different temperature rating. Selecting the appropriate insulation class ensures the transformer can withstand the operating temperatures without insulation degradation. Sixthly, the impedance is the opposition to the flow of alternating current, typically expressed as a percentage. The impedance of the transformer affects the voltage regulation and short-circuit current. Seventhly, the regulation describes the change in secondary voltage from no load to full load conditions, usually expressed as a percentage. Lower regulation values indicate better voltage stability under varying load conditions. Eighthly, the inrush current is the peak current that flows when the transformer is initially energized. This current can be significantly higher than the normal operating current and must be considered when selecting overcurrent protection devices. Ninthly, the efficiency represents the ratio of output power to input power, expressed as a percentage. Higher efficiency transformers minimize energy losses and reduce operating costs. Tenthly, the standards compliance indicates the standards the transformer meets, such as ULC and CSA standards. Compliance with these standards ensures the transformer has been tested and certified for safety and performance. When selecting a control transformer, it is important to consider the ambient temperature in which the transformer will be operating. The ambient temperature is the temperature of the air surrounding the transformer. If the ambient temperature is too high, the transformer may overheat and fail. Control transformers are typically designed to operate in ambient temperatures up to 40 degrees Celsius, also known as 104 degrees Fahrenheit. If the transformer will be operating in a higher ambient temperature, it may be necessary to direct the transformer's volt-amps rating. Dirting means reducing the volt-amps rating of the transformer to compensate for the higher ambient temperature. The amount of dirting required will depend on the specific transformer and the ambient temperature. It is also important to consider the altitude at which the transformer will be operating. The altitude is the height above sea level. At higher altitudes, the air is thinner and less dense. This can affect the transformer's ability to dissipate heat. Control transformers are typically designed to operate at altitudes up to 1,000 meters, also known as 3,300 feet. If the transformer will be operating at a higher altitude, it may be necessary to direct the transformer's volt-amps rating. The amount of directing required will depend on the specific transformer and the altitude. When installing a control transformer, It is important to ensure that the transformer is properly grounded. Grounding is the connection of the transformer's metal enclosure to earth. This helps to protect personnel from electrical shock in the event of a fault. The grounding conductor should be sized according to the applicable electrical codes and standards. It is also important to ensure that the transformer is properly ventilated. Ventilation is the circulation of air around the transformer. This helps to dissipate heat and prevent the transformer from overheating. The transformer should be installed in a location where there is adequate airflow. If the transformer is installed in an enclosure, the enclosure should be vented to allow for air circulation. When troubleshooting a control transformer, there are several things to check. Firstly, check the input voltage to the transformer. Make sure that the input voltage is within the specified range. Secondly, check the output voltage of the transformer. Make sure that the output voltage is within the specified range. Thirdly, check the fuse or circuit breaker on the primary side of the transformer. If the fuse or circuit breaker is tripped, replace it with a new fuse or circuit breaker of the same size and type. Fourthly, check the wiring connections to the transformer. Make sure that all of the wiring connections are tight and secure. Fifthly, check the transformer for any signs of damage, such as cracked insulation, loose connections, or overheating. If you find any signs of damage, replace the transformer. Control transformers are robust devices, but they can fail due to various reasons. Overloading the transformer beyond its volt amps rating can cause overheating and insulation breakdown. Sustained overvoltage can stress the insulation and shorten the transformer's lifespan. Frequent short circuits in the connected control circuit can damage the transformer windings. Excessive ambient temperature can reduce the transformer's ability to dissipate heat. Moisture or contaminants can corrode the windings and insulation. Loose connections can cause arcing and overheating. Physical damage from impact or vibration can compromise the transformer's structural integrity. To prevent failures, it is essential to select a transformer with adequate capacity for the intended load. Protect it from overvoltage and short circuits, maintain proper ventilation, keep it clean and dry, and ensure all connections are tight. Regular inspections and preventative maintenance can help identify and address potential problems before they lead to failure. Understanding the causes of failure and implementing preventive measures can significantly extend the life of a control transformer.